Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
Welcome to The Explainer. Today, we're decoding one of the absolute most incredible anomalies in the physical world, dinitrogen. I mean, it's literally all around us, right? It makes up most of the air we breathe, and yet its chemical secrets are locked away behind some of the strongest forces in nature. Okay, let's dive right into this. Here's our roadmap for today. First, the dinitrogen molecular vault. Then, breaking the triple bond, followed by biological and ecological fixation. After that, we'll hit coordination and binary compounds, extreme phases and polymers, and finally wrap up with technology and strategic outlook. Section 1, the dinitrogen molecular vault. So let's introduce the central villain of our narrative, the stubbornly inert dinitrogen molecule. Even with its high electronegativity, it behaves almost like a noble gas. Why? Well, it all comes down to this number, 945.33 kilojoules per mole. That is the massive bond dissociation energy of the nitrogen-nitrogen triple bond. Its quantum architecture creates this huge 10.82 electron-volt gap between its highest occupied and lowest unoccupied molecular orbitals. Think of it like an unbridgeable canyon. Without some serious thermal or catalytic intervention, electrons just cannot jump that gap. It's essentially an unbreakable vault. And to really put this into perspective, we can compare nitrogen to its downstairs neighbor on the periodic table, phosphorus. This brilliantly illustrates the quantum anomaly we're dealing with. Because nitrogen is restricted to tiny 2s and 2p valence orbitals, they overlap perfectly to form that incredibly strong triple bond, leaving it as a nonpolar inert gas. But phosphorus? It has a much larger radius. It just can't overlap effectively enough for a triple bond, so instead it forms single-bonded networks, hanging out as a reactive solid, like white or black phosphorus. Actually, nitrogen literally hates being in a single-bonded chain. The weak single bonds repel each other so much that nitrogen polymers desperately want to snap back into a diatomic gas.
Section 2, breaking the triple bond. Because nitrogen is so stubborn, human ingenuity has historically relied on sheer brute force to crack it open. For over a century, our primary weapon has been the industrial Haber-Bosch process. To make ammonia, we basically blast the gas with up to 500 degrees Celsius of heat and crush it under 250 atmospheres of pressure. But the real magic, that happens on the surface of iron or ruthenium catalysts. Following what's called the Langmuir-Hinselwood pathway, specific open iron crystal facets, like Fe111, transfer electron density directly into dinitrogen's antibonding orbitals. It literally pumps electrons into the bond until it stretches out and cleaves completely apart.
But look at how far synthetic inorganic chemistry has evolved. We aren't just relying on hot, high-pressure bulk iron anymore. Scientists like Richard Schrock developed a molybdenum catalyst that reduces nitrogen at just 25 degrees Celsius. Then Nishibayashi achieved massive turnover numbers using pincer ligands, and Jonas Peters even proved we can catalytically reduce nitrogen to ammonia at minus 78 degrees Celsius using a single iron center supported by boron ligands. We've officially moved from the sledgehammer to the scalpel.
Now, you might be wondering, if humans can just now do this at room temperature in a high-tech lab, how on earth has nature been breaking this exact same bond out in the dirt without 500 degrees of heat for billions of years?
Section 3, biological and ecological fixation. Well, it turns out half of all the fixed nitrogen on Earth is processed quietly at ambient temperatures by microscopic life. The hero here is an enzyme called nitrogenase, and its active heart is this incredibly complex structure, the iron-molybdenum cofactor, or FMO-Co. It's a metal cluster featuring iron, sulfur, and molybdenum. But the absolute most fascinating part is sitting right smack in the center, a single hexacoordinate interstitial carbide atom. That central carbon atom acts like a structural anchor, stabilizing the entire cluster while it juggles multiple electrons.
Let's walk through how this builds a catalytic cycle, which is described by the Thornley Low kinetic scheme. The enzyme pumps electrons and protons into the cofactors step by step. When it hits the E4 state, which holds 4 electrons and 4 protons, it reaches what we call the Janus intermediate. Like the two-faced Roman god, this state has a choice to make. To actually bind the incoming nitrogen gas, the cofactor has to do an obligatory reductive elimination. Basically, it kicks out hydrogen gas. It breathes out H2, which opens up the cluster to grab the nitrogen molecule, eventually reducing it all the way down into 2 ammonia molecules.
But, biology doesn't just fix nitrogen, it also recycles it. A massive chunk of the global ocean cycle relies on marine bacteria performing ANMOX, that's anaerobic ammonium oxidation. These bacteria convert ammonium and nitrate back into dinitrogen gas. And to do this, they make a highly toxic rocket fuel intermediate called hydrazine. To avoid poisoning themselves, they lock these enzymes inside a specialized organelle called the anamoxisome. This thing is sealed tight by an incredibly dense membrane made of laterine lipids, literally lipids shaped like tiny ladders to prevent any toxic leaks. Nature is just wild.
Section 4. Coordination and binary compounds. Once you understand how to manipulate that triple bond, an entire chemical zoo opens up for us. When chemists attach dinitrogen to transition metals, it primarily docks in one of 3 ways: at one end, bridging across 2 metals, or laying flat in a side-on coordination. That side-on mode is especially cool because the metal essentially pumps so much electron density back into the nitrogen's antibonding orbitals that the internal triple bond drastically elongates and weakens, totally priming it for a chemical attack. And from those manipulated states, we get a huge variety of binary compounds, spanning some incredible oxidation states. You have ammonia at -3, you've got hydrazine at -2, which, fun fact, is so energetically unstable that it's used as a hypergolic rocket propellant. On the positive side, you have nitric oxide, a diatomic radical that's absolutely crucial for human blood vessel signaling, all the way up to dinitrogen pentoxide at +5, which is used as a powerful nitrating agent. Section 5. Extreme phases in polymers. All right, now for the climax of our explainer. What happens when we push nitrogen to the absolute limits of thermodynamics? We get this: cubic gauche nitrogen. Remember earlier when we said nitrogen hates being in single bonds? Well, in 2004, scientists trapped it in a diamond anvil cell, cranked the pressure to over 110 gigapascals, that is over 1,000,000 times atmospheric pressure, and blasted it with a laser at 2000 Kelvin. The extreme physics completely collapsed the triple bonds, forcing the nitrogen into a single-bonded, diamond-like cubic lattice. Looking at the solid allotropes, you can cool nitrogen down to a solid at 1 atmosphere, getting a cubic alpha phase or a hexagonal beta phase, where it's still just normal diatomic molecules vibrating around. But cross that 110 gigapascals threshold, and the physical rules completely rewrite themselves into cubic gauche. Push it even further, past 120 gigapascals, and it forms layered polymeric networks. It's a whole new world at those extreme pressures. The implication of that forced structure is massive. If you have this single-bonded cubic gauche nitrogen and you let the pressure off, it desperately snaps back into dinitrogen gas. And when it does, it releases roughly 10 to 11 kilojoules per gram of energy. That makes it an explosive 5 times more powerful than TNT. And because the only byproduct is safe, breathable nitrogen gas, it is widely considered the holy grail of environmentally benign, high-energy density materials. Section 6. Technology and Strategic Outlook. Let's bring all this extreme physics back down to Earth. How does this actually impact our daily lives? Well, the inertness and cold temperatures of nitrogen drive modern industry. Liquid nitrogen boils at 77 Kelvin. In cryobiology, this rapid cooling achieves vitrification, turning water into a glassy solid without forming ice crystals, which safely preserves stem cells. In manufacturing, we use gaseous nitrogen to purge chemical tanks, displace oxygen to stop food spoilage, and provide the ultra-high purity environments necessary to fabricate the silicon semiconductors in the very device you are using right now. So the strategic outlook here is incredibly exciting. Researchers are now using plasma-enhanced chemical vapor deposition and precursor chemistry to try and stabilize that explosive cubic gauche nitrogen at ambient, everyday pressures.
And at the exact same time, by emulating the biological genius of the nitrogenase enzyme we talked about, we are slowly figuring out how to bypass the massive energy demands of the Haber-Bosch process so we can feed the world much more sustainably. We've seen how the unbreakable triple bond can be cracked by industrial heat, enzyme machinery, and millions of atmospheres of pressure. But it leaves us with this final thought. If we are on the verge of synthesizing high-energy polymeric nitrogen at ambient pressures, breaking one of the most stubborn thermodynamic rules we know of, what other unbreakable rules of chemistry will human ingenuity rewrite next? Thank you so much for joining me on this explainer, and keep questioning the mechanics of our fascinating world.
Like what you share.
This website makes learning so easy. I found all my resources here.
Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.